All right, so now we come to a very interesting unit of circular motion and universal gravitation, one of my favorite units to cover. So here's some motives for why we're going to be looking at this unit. So first off, we've been studying throughout the year objects that move in a straight line, and specifically acceleration in that straight line, slowing down and speeding up. But we've also seen that objects can accelerate one other way by changing direction. So specifically, by changing direction, this leads us to look at circular motion and what we call acceleration in circular motion, specifically what we call centripetal acceleration. The reason why we waited up until this point is because circular motion also relies a little bit on an understanding of rotational motion, since an object moving in a circle could also be considered rotating. And in addition, we do need rotational motion combined with circular motion to look at the further topics down the line in this unit, which is when we look at universal gravitation, aka essentially a light introduction to astrophysics. So today we'll be looking at circular motion and how we can approach circular motion based on the topics we have studied so far in this course. So the first thing we need to establish with circular motion is what we call orbital speed, okay? Orbital speed v describes the rate at which the object completes one revolution of a path, aka one successful orbit. So let's say we have an object S that rotates or moves around a circle around an object E. So let's say that S is a satellite and this is Earth E right here. One successful orbit is all the way around one revolution, okay? The time it takes to complete one whole orbit is called the orbital period T. So just like we saw that there's a period for waves and there's a period for spring motion, there's also a period for objects that are moving in orbits, which makes sense because an orbit is a periodic repetitive motion, just the same ways that springs and waves and pendulums are periodic motions as well. However, as we'll see and as we will discuss in class, objects moving in orbits are not harmonic. It's not an example of a harmonic motion. It's strictly a periodic motion. So orbital speed, to reiterate, is the rate at which an object completes one revolution of an orbital path. And the time it takes to complete this whole orbital path is called the orbital period T. So the relationship we get between our orbital period V and the orbital speed V and the orbital period capital T is V equals 2 pi r divided by t. This equation is not on your equation sheet, so it must be memorized. However, there's not a whole lot of memorization that has to go into it because it comes from the fact that speed is defined as distance divided by time. So the distance traveled on one full orbit is equal to the circumference of this orbit, which is 2 pi r. And then the time that you're dividing by is the period, the time it takes to complete one whole orbit. So for orbital speed, we're going to get v equals 2 pi r divided by the orbital period t. So we have this nice relationship here. Down the line, when we get into astrophysics and orbital mechanics, we'll see there's a different equation for orbital speed depending on the gravitational field of a planet. So this equation right here holds for any orbits, any specific orbit, any object that's moving in a circle, and then the equation we get down the line for orbital speed will apply for objects that are in orbits due to the force due to gravity of a planet. So let's take a look at centripetal force and centripetal acceleration, okay? So recall that there's a third form of acceleration, an object changes direction. So recall that velocity depends on both speed and direction, so we can slow down, speed up, or change direction to accelerate, okay? So in order for an object to change direction, a force must act perpendicular to the object's current path. So just as for an object to speed up requires a force to act in the same direction as the object's motion, and to slow down requires a force to act opposite the direction of the object's motion, in order to change direction, a force must act perpendicular to the object's current path. The idea being, again, is that the force is a cause, and the acceleration, the change in motion, is an effect. So force is a cause, acceleration is effect. So if we want to accelerate by changing direction, that requires a force that pushes us in the direction of motion that we want to go, which means the force has to be pushing perpendicular to our direction of motion. Okay? So inertia and momentum of our object, however. So if we look at this v right here, this v is perpendicular to our force. And if we draw a circle that has a force as the radius, this v is going to be tangential to our circle. All right. The idea here is that the inertial momentum will want to keep the object moving forward instead of moving in a circular path. So the result will be a gradual change in direction, a compromise between the acting force and the inertia of the car. So the force ideally would want our car to go perfectly to the left. Or if the force is acting to the right, perfectly to the right. However, because our car has inertia and wants to keep heading in the direction that our velocity is pointing, we're not going to head completely to the left. So we're going to have a nice compromise where instead we're going to gradually change direction in a circular path here. Now that's kind of a watered down way of thinking about it, and the inner physicist in me is kind of kicking myself over this, but it's a useful way of thinking about it and getting introduced to this concept. So as a result, again, this results in an object moving a circular path until the force ceases to act, okay? And then we'll take a look at the case of what happens if a force ceases to act in class tomorrow with some critical thinking and problems, and some problems posed to the class. Ooh, and it lights up again. So, what do we call this force that acts perpendicular and causes us to move in a circular path? We call this centripetal force, okay? So the centripetal force is any force or sum of forces that act to cause circular motion, to cause a change in direction, okay? The forces act radially and towards the center of the circular path. Radially means along the radius and towards the center of the circular path, okay? So please note that the big thing is that the centripetal force is not actual force like tension or force through gravity. It is a label given to the force or sum of forces causing circular motion. So just as we have net force in x and y direction not being an actual force, but just being a sum of forces in the x or y direction, centripetal force is just the net force that causes circular motion. So it's not an actual force itself. So for example, okay, in example A right here, if we have a ball that's swinging on a string, the orbit in circular motion is caused by the tension. So the tension is what acts as our centripetal force here. In case B, if we have a person or a car that's turning on a road, the force due to friction between the road and tires is responsible for the car turning and going in a circular path. So the centripetal force in this case is supplied by the force due to friction. And then if we have a person on a roller coaster, what's keeping the person going on the roller coaster right here in its path is specifically the normal force and the force due to gravity at this specific point. So the sum of the normal force and the force due to gravity at this specific point is responsible for keeping our object on a circular path. So the centripetal force in this case is the sum of the normal force and the force due to gravity acting at this specific point. And then lastly, if we have, say, a planet orbiting a star, like the Earth orbiting the Sun, the force due to gravity between the Earth and the Sun, specifically the force due to gravity of the Sun acting on the Earth, is what keeps the Earth in a circular orbit. So the force due to gravity from the Sun on the Earth is what supplies centripetal force in this case. And we'll study this case in more detail the rest of this unit right here, where we have the force due to gravity acting as our centripetal force. And this will act as our segue into astrophysics. So let's get an equation for centripetal acceleration then, okay? So centripetal acceleration, the first thing we need to take note of, okay, is that if our object travels in a circle, in a circular path right here, it's going to travel with a radius r from the center of our circle. So our path that traced out right here is going to set up a triangle where we have the legs of our triangle are r, and then the base of our triangle is equal to the path traveled by our object in some time t. Well, the path traveled in this time t right here is going to be our velocity times time. So this arc length of our circle is going to be velocity times time right here, the path that we've traveled in this time t right here. All right. At the same time right here, our velocity vector at point A is going to point in this direction, but at point B, our velocity vector is going to point in a new direction at point B. So what we can do is we can connect the velocity vector at point B and the velocity vector at point A by their tails right here, and we can use this to set up a new triangle where the base of our triangle is the change in velocity. Recall that the change in a vector, specifically the velocity vector, is given by the space between the vector at some time A and some time B when we connect the vectors by tails. If all this seems very esoteric and abstract, again, this does draw on a lot of math, so if at the end of the day you're still a little bit confused by it, I got news for you. You just need to understand, you just need to know the result that we get at the end of it, okay? So here, what's going to happen is after doing a little bit of trigonometry and a little bit of geometry here, a little bit of reasoning geometry, you can actually show that this triangle right here is actually similar to this triangle. All right, so what we're going to get as a result is that we're going to get the base of this triangle divided by one of its legs, delta v divided by v, is going to be equal to the base of this triangle, VT, divided by the leg of this triangle, which is R right here, okay? So we can do that because these are similar triangles right here, and thus the ratio of the base to leg is going to be the same for both triangles, okay? So this is where we're at right here. So now what we can do is we can solve this equation for delta V, which gives us V squared, which gives us delta V equals V squared times T divided by R. So now what we can do right here is we can divide both sides by T right here. Like what happens right here, we divide both sides by T, which gives us delta V divided by T equals V squared over R. But if we recognize delta V divided by T is just our definition equation for acceleration, so we have that our centripetal acceleration is equal to the speed squared of our object on the circle divided by r, where again our speed at each point is going to be tangential to our circle, because by Newton's first law, that's how our object wants to move at each point, is tangential to circle and keep moving on a straight path. All right, so the centripetal acceleration is equal to our speed at each point of the circle squared divided by the distance we are from the center of our circle. Okay, so centripetal acceleration is equal to v squared over r. A nice thing is you don't have to memorize this equation because it is on the equation sheet. Now, a similar form that is not on the equation sheet is the centripetal acceleration equals the angular velocity squared divided by r. So we could treat this as an object that is rotating with an angular velocity, and we can use a form of centripetal acceleration with an angular velocity or angular speed. To get this form right here, all we do is we take v and replace it with omega times r, the conversion from angular to linear velocity, and that's going to give us omega squared times r divided by r, or omega squared times r after you do a little bit of algebra and simplifications. So this equation right here you do not need to know because it's on the equation sheet. This equation right here you do need to know because it's not on the equation sheet. Okay? So Newton's second law in centripetal motion. So dealing with problems of Newton's second law for centripetal motion is the same as we've done going all the way back to Unit 2, except now we have two caveats. All right, we're going to sum our forces together. We're going to set it equal to mass times centripetal acceleration, except we're going to replace centripetal acceleration with v squared over r. So that's the thing that you always need to do with these problems here, okay? The second thing is now we're going to set up our coordinate system. So in this case, forces that are acting radially inward, aka towards the center of our circle, are going to be positive, and forces that are acting radially outward, aka away from the center, are going to be negative. So that's how we're going to treat forces in our new coordinate system here, okay? So the problem solving process from Unit 2 still applies, but we now need to make these two caveats for Newton's second law problems involving centripetal motion. So let's take a look at an example problem here, just a simple example problem because I realize these concepts here might be a little bit abstract and esoteric, as all things in physics tend to be at this point. Abstract and esoteric is a word I've used quite a lot throughout the year. So let's take a look at a simple problem and then we'll do more advanced problems together in class. So a 3 kilogram mass attached to a light string rotates in a circular path on a horizontal frictionless table. The radius of the path is 0.8 meters. What is the tension of the rope if the speed of the mass is 2 meters per second? Okay, so what we're going to do here is we're going to take the perspective of being behind our mass right here, so that we're going to see our mass, we're going to be behind our mass, and then the tension that keeps our mass moving in a circle is going to be acting to the left, with the center of our circle being right here. Okay, so that's how we're going to view things here with these circular motion problems. Okay. So in this case, tension is going to act to the left. Here's our table. We're going to have the force of gravity acting downwards, and then we're going to have the normal force acting upwards from the table on our object. Okay? So this is what our free body diagram looks like here. So now we move to number 2, where we sum forces in the radial direction. Okay, again, these forces, normal force and force due to gravity, are not acting in the radial direction, so we do not have to worry about them when we sum our forces acting in the radial direction. In this case, the only force that's acting in the radial direction is our tension T. So we're going to have T equals m times our centripetal acceleration, where we replace our centripetal acceleration with v squared over r. Again, tension is going to be positive here since it acts radially inward. It acts towards the center of our circle. If there was a force that acted outward right here, okay, that would be a negative force because it's going to be acting outward away from our center of our circle. So now we solve for our unknown quantity t, which in this case just amounts to us plugging in some variables, so 3 kilograms for our mass, 2 meters per second for our speed, and 0.8 meters for our radius, which is going to give us a tension of 15 newtons. So we'll look at circular motion in more detail in class tomorrow and discuss some misconceptions, some major misconceptions with circular motion. But for right now, here are the basic concepts, problem-solving processes, and equations that you need to know in order to become prepared for class tomorrow.